Jai Hind everyone. I am Pankaj Kumar and today's video about the carbohydrate lecture. Carbohydrate. It is a series of videos, and this is the first video of that series. And this series, what we are going to read about the 3 points which we are going to follow in this series of lecture. First, we are going to see monosaccharide and disaccharide. Monosaccharides and disaccharides. Second, we'll read the next video. We'll read about the polysaccharide. And in third video, we'll read glycoconjugates. What is the meaning of glycoconjugates? Actually, it is proteoglycan, glycoprotein, glycolipids. All are the glycoconjugates we are going to read. So let's begin with the first topic, monosaccharide and disaccharide. Whenever we are saying the term carbohydrate, so what is comes in your mind? Sugar. And where this sugar is synthesized, C6H12O6, it is synthesized in the plant. Do you know this sugar is synthesized by daily using of 100 billions of CO2 and H2O, 100 billions of CO2 and H2O, 100 billions ton, metric ton, okay? Of CO2 and H2O are converted into the glucose, and this glucose is converted into the cellulose or other plant products. Plant products. So this is a very fascinating thing. Carbohydrate, the term you will see here, it's come from the carbs. What does it mean? Carbon, definitely. And hydrate, what does it mean? There will be water. What they will form? They will form two type of compound. Either they will form aldehyde, CHO group, or they can form CO group. Okay, this is what? Aldehyde. Or this is what? Ketone group. So carbohydrate is nothing, just a polyhydroxy ketone or polyhydroxyaldehyde. So you can name it, either it is a polyhydroxy ketone or polyhydroxyaldehyde. Simple meaning only. So usually the carbohydrate have the formulas like the simple formula is what is CH2. Okay, where what is the number of the carb? It can be the digit carbon. How many carbons are there? If there will be one carbon, you can put a one and then you'll multiply two, two, four like this. Okay. So can we put one also? So n cannot be equal to the one or two, and should be either uh, greater than or equal to 3. There is a no carbohydrate which is like CH2O or CH C2H4O2. Okay, that type of carbon is not existing. Carbohydrate are not existing. So the simplest form of the carbohydrate is what? Triose. What it is? Triose only. Okay. So does it exist for the every carbohydrate? The formula which is written here, it is not. The some carbohydrate have some carbohydrate does have nitrogen, sulfur, or phosphorus or something. Okay, so this hence it's not a universal formula. It's not universal formula. This is just a simple formula. We can use it for the carbohydrate, but it is not a for every carbohydrate. Got it? We used to say saccharide for the for the sugars. Okay, so exactly it's the meaning of the saccharide is sugar only. So monosaccharide, polysaccharide, disaccharides. Meaning of saccharide is what? Sugar. It comes from the Greek word. It is called saccharin. And what is the meaning of this? It is a sugar. So for the ease of our studies, we divided the carbohydrate into two or three parts. Okay. So carbohydrate having three parts, three types. The first is what? Monosaccharide. Second is what? Disaccharide. And third is what? Or we can write it here. Not di. Instead of di, we should write oligosaccharide. Oligosaccharide. And here it is polysaccharide. So monosaccharide, disaccharide, oligosaccharides are uh, the important component of the carbohydrate or the types of the carbohydrate which we are going to cover in the coming videos. So monosaccharide are the sweetest. It will be give the sweet taste usually, and the simplest carbon monosaccharide is the glucose. Polysaccharide is usually non-sweet. Okay, and this will help in the modification of protein. These things help in the modification of protein or lipid. We'll see all the details for the oligosaccharide. Let's begin with the monosaccharide. Monosaccharide is the most important because it is the unit of all the carbohydrate. If you see the monosaccharide will have the it is features like a non-crystal. It is a non-crystalline, colorless, colorless, non-crystalline, colorless, and non-sweet. Sorry, sweet in taste. Okay, sweet in taste. These are the small importance about the monosaccharide. In monosaccharide, there will be hydroxyl group. There will be hydroxyl group at chiral carbon. What do you mean by the chiral center or carbon? So some any carbon which will have the different type of bonds or functional groups. So suppose this carbon I am going to draw one hydrogen, one OH group, one CH3, and again and make any R group, any functional group. Non-benzene. If you see here, what you're going to see, there is a no same functional groups are there in the carbon. This carbon have a different functional group. One side OH, one side H, one side methyl, one side ethyl. So this will be called as a chiral center. What it is called? This will called as a chiral center. So the chiral center does must have the OH group in the monosaccharide. So so you can see here whenever there will be aldehyde, what this? If it is aldehyde at CHO group at terminal, if it is at terminal, then it will be the aldose. Then it will be what? Aldose. And again, if carbonyl group, again, if a carbonyl group in mid, that means what? It will be somewhere in the middle of the chain or middle of the chain. Then it will form a keto group. What? Keto, and that compound will called as a ketose. So it's basically, just want to say, aldehyde will be always at the at the terminals of the chain, and ketones will be there in the middle of the chain. So here is the important thing. So most of the monosaccharide have what? The chiral compound, except what? Except this dihydroxyacetone. So except dihydroxyacetone, all the monosaccharide have the chiral carbon, and that's why they can form. They will be able to rotate the rays. They will able to rotate the rays, and they will form the optical isomers. That's why we are called it. They are optically active. So if they will able to form, if they are able to like rotate the polarized lights, so we can say they are optically active. Or in simple terms, if I will say, uh, it will form a mirror image which is not similar in both compounds. Like in mirror, your right hand will be the left hand of that mirror image. So uh, like that, if you'll see the glyceraldehyde, so you'll find in the glyceraldehyde the carbon of OH, CH2H, and CH. Here is the mirror. Sorry. So what you'll find here, everything will be correct only. Everything will be correct except one position. These vertical positions will be same, but you will find the hydrogen will go backside and the OH will come this side. Okay, this is the change because of the mirror image, that is called optically active. What if there will be both hydrogen only? Here it is also hydrogen. Then here also you will get the hydrogen. Then in that case you will unable to find the change. So that will be optically inactive. Okay. Hopes you understood this thing. Now we'll see the stereoisomers. So what is the stereoisomers like? They have the structural differences, and the chemical formula will be same. Okay, so stereoisomers are, is it very important for the life? Yes, it is very important for the life, because they will define the activities of the enzymes and all. Okay, so remember it, like number of stereoisomer, how much stereoisomer can be found from a compound. So it is not universal, again it is just for generalized method. It is around 2 power n. And what is the meaning of n? Where n is, number of chiral center, number of chiral center, or you can say chiral carbons. So that will give you the number of stereoisomer. If I will ask you any compound in which 3 chiral carbons are there, so how many stereoisomer will form? Total 8. Yes or no? Correct only. Like that you can find it down. And how you'll find it in a compound? How many chiral carbons are there? You have to like find by your own intelligence. Like next we'll see some carbons which will have the different groups. Okay, like that we will find. So as you can see here, that two sugars only differ in configuration around only one carbon called epimer. Okay, so you can see in this diagram that mannose, D-mannose and D-glucose having uh, a configurational change difference between the second carbon compound. Okay, in this, so hydroxyl group is at the right side of this mannose. You don't have to imagine according to your view. From your side you have to see that OH from the compound side. Okay, so if you'll stand here in between, here in center of this, that OH will be on the right side. Okay, and sorry, you can imagine from your side, so OH will be on the left side. Okay, and here you will find the OH will be on the right side. For now you can see right this, like that. But in the same case, if you'll see the D-glucose and the D-galactose, the OH will be having a different configuration in the glucose and galactose at the fourth carbon. Okay, so that is what the epimer called. Okay, so glucose is the epimer of the mannose, as well as the glucose is the epimer of the galactose, but the carbon position will be different for the both type of epimer. But mannose and galactose are not the epimer of each other. Got it? So what we'll call it, we can call it as a isomer, but not as an epimer. So this is done. Now we'll see the how the rings will be occur. Actually, the carbons which you are seeing here, they that will be not in the chain. They want to be in the ring structure. Why? It will give them the more stability. So if you'll see, the ring structure will be formed by the intermediate structure. Intermediate structure. So usually the aldehyde group. First case we are seeing for the aldehyde group. So aldehyde group will bind with the any hydroxyl group. So this is R2, this is R1, and it will give R1, and it will attack here OR2, and again here what will be there? Hydrogen. So this is what? This is called as a hemiacetal. Okay, hemiacetal. Why it is called hemiacetal? because we are bringing this hemiacetal from the aldehyde reacted with the what? Hydroxy group, or sorry, reacted with the alcohol. Now finally you will got the hemiacetal. Hemiacetal will again, this is the intermediate. Now it will give you the acetal. What it will give you? It will give you the acetal by adding of the one more alcohol group. Suppose again you will get OR3 here, and then R1, and here H. So it is what? Acetal. If we'll go back, it is a reversible reaction, so it can convert it into hemiacetal as well as by removing the alcohol with the R3. So this is the way how they will going to form a ring. In this we didn't find the ring, but alcohol will react with the aldehyde or the ketone, then it will go is for forming of the ring. Now the rings will be of two type. Now the reaction we seen with the aldehyde, now we are going to see the reaction with the ketone. So ketone body will looks like this. Here R1 and here one R2. It react with one alcohol, and you can take it as a R3, and it is a ketone. It will give you what? It will give us the hemiketal. Correct. Very nice. It will give us the hemiketal R1, R2, O3, and here you will get what? Which? Okay. This is what? This is your hemiketal. Now it can give you the again. It will give you the ketal group. Okay. By giving this. For that you need again one alcohol. OH R4 you will give now. So you will get OR4, OR3, here OR, sorry, R1, not OR. Here you will get the R2. It is already there from the beginning. Okay. So this is all about. By this way only we will understand the how the pyranose or furanose ring will be formed. Like it is a basic in which we are going to understand the alcohol and aldehyde or a ketone will react, and it will give you the following hemiketal or hemiacetal group. Okay. So So usually we are seeing the glucose is a complete six carbon compound ring. So the six carbon compound ring is used to called as a pyranose. Okay, it is six carbon ring. So example is what? Glucose. But if we'll see the same six carbon compound, but it is forming a five carbon root ring, furanose. Furane or furanose you can say. Again, it is forming five carbon ring instead of six carbon. What is the example? Fructose. Why we cannot write a ribulose? Because ribose itself it is a 5 carbon compound. Can we write ribulose as a furanose ring? No. It is itself it is a 5 carbon compound and it is forming a 5 carbon ring only. Okay, now it's not forming 5 carbon ring. One, two, three, four, 4 carbon ring with one oxygen. Okay. So hope you understood this. Now we are going to see the understand the meaning of the anomeric carbon and all. Just now we seen the hemiacetal and hemiketal. So that will give you the concept that what is the anomeric carbon. So isomeric form of monosaccharide that differ only in their configuration about the hemiacetal hemiketal carbon atom is called as a anomeric carbon. So hopes you understood the meaning of anomeric carbon. And now I just want to show you the pyranose and furan ring. So you can see this is a fructose. This is a alpha D fructose and alpha. This is alpha D glucopyranose, fructofuranose. Okay. So this is a beta D glucopyranose and this is a beta D fructofuranose. Why we are saying it is a alpha, one is the beta? Can you find it the differences in that? Why we are saying it is a any different? What difference you found in that? You just stop the videos and find it. So the main difference which I found, the plane changes here. Okay. So the plane change here, the CH2OH null came downside. So whenever the change will be occur in the plane, then it is from the beta, and the same will be in the case of the pyranose also. But why it is called as a D, or sometimes it is written as a L form? So usually in nature, the D form will be more in the D form glucose will be more in the nature instead of L form. So L form is not there in nature more. Why we don't know the reason, because D form is, but D form is the more in the nature. So D fructofuranose or is the 5 carbon 5 ring compound. Okay, this here, and pyranose is 6 ring compound. So hopes you understood here that 6 carbon, sorry, 6 carbon I'm saying again. I earlier I said 6 carbon, I think so. This is 6 compound rings. Okay, and this is a 5 member ring. So this is the difference in the pyrene and furanose. Now we are seeing the varieties of the disaccharide. So kindly keep fast forward this video because I just want to complete this topic and it will be a little long. So derivatives of the hexose will be what? So replacing of the hydroxyl group from the second carbon from the parent compound with the amino group gives you the following. So suppose you're replacing the second carbon. Let me just add one photo. So the simplest sugar is what? The glucose. Okay. So you can see this is the simplest form of the sugar here. And there is a second carbon. Okay. Second position. First, second. Second carbon. What is there? Here it is OH group. Here it is OH group and it is replaced by what? It is replaced by the NH2. So this ammonia group came instead of OH, that is A1 derivative, and that will form you the glucosamine. Okay. So the same it is forming the glucosamine. If there will be one acyl group will be added here. This acyl group is added at the amino group with the amino group. Then it is forming an acyl glucosamine, beta O glucosamine. Sorry, beta D glucosamine, and it is found in the where? It is found in the cell wall of the prokaryotes. Remember it. It is found in the cell wall of the prokaryote. Now you can find in the beta D glucose 6 phosphate. So in this case, again you are removing the OH group, replacing the OH group with the ammonia group, and then you are adding what? acetyl group. So it is forming what? The muramic or N-acetyl muramic acid. This is the very important thing. Later you can see in this case beta galactosamine or beta manosamine. So the same structural difference is there, like configurational difference. The plane changes here to here, then it is forming galactosamine to the manosamine. Okay. Anything else difference you can find it here? Amino group and OH. Okay, now fine. Now here you just see the beta D glu- uh, gluconic acid. So oxidation of the aldehyde carbonyl carbon of the glucose produces the gluconic acid. Where is the aldehyde? Let me see here. Glucuronate. So finally, you are getting the beta glucuronate, which is forming the glucone lactone, and this is a very important form for the recognition or the cell surface proteins, which will help in the recognition on the cell surface. N-acetyl neuramic acid is the another name of the sialic acid. So these are all the derivative of the sugar. So this is the amino sugar, this is the deoxy sugar, and this is the acidic sugars. Just you follow this thing. What I am going to write now. What this is the important thing. So glucose OH replace from C2 carbon. Okay, C2 carbon, and it gives replace C2 OH replace ammonia. Okay, Ammon amino acid. Sorry, not ammonia. Amino acid. Amino acid replace OH. It's C2 carbon. Okay, and it can give what? It can give glucosamine. If you add acetyl, then it is giving what? An acetyl glucosamine. Okay, and acetyl glucosamine. And this N-acetyl glucosamine is where it is helping the prokaryotic. It is forming the prokaryotic cell wall. Prokaryotic cell wall. Okay. Remember it. Mycoplasma don't have the cell wall. It is also prokaryotic, but don't have the cell wall. Another is what? Galactosamine. It will form what? Galactosamine. Okay. Or it can change into what? It can change into the manosamine. Okay. Galactosamine can change into the amine. And manosamine it will condense with the acetyl group. If it is added with the acetyl condensation, then it will give you the N-acetyl glucosamine. It will give you the one N-acetyl glucosamine. Finally, we reached here. Yeah. By this way also you can go, or the same glucosamine will give the galactosamine, then it will give the N-acetyl glucosamine. Same only. So oxidation of the aldehyde carbonyl carbon of a glucose produce gluconic acid. What is happening here? If the aldehyde oxygen aldehyde oxidation. Okay, aldehyde oxidation of glucose. It will give you what? Gluconic acid. So we are seeing the derivatives. And what is the use of this gluconic acid? The very important use of this gluconic acid is what? The counter ion. Okay, it act as counter ion. What does it mean? Whenever you will see in most of the reaction, there will be any uh, there will be metal ions will be used. So for the drugs also, in the drug, there will be some charges there will be some charges like calcium plus 2 in case of the quinone. Okay, so this charges have to be balanced. So this will be balanced charge is balanced by balanced by gluconic acid. One more, if there is a oxidation at C6 carbon oxidation, if this will be occur, so glucose will give you what? At 6 uh, oxidation will occur of glucose, then glucose will give you the all will give you the uronic acid. Okay, uronic acid. Every 6 carbon, if there is a oxidation, then it will give the uronic acid. Okay, you mentioned here gluconic acid. So in case of glucose, it will called as a glucouronic. Glucouronic. In case of lactose, it will called as a galactouronic. Like that, in case of the mannose, it will called as a manouronic. So just now we formed uronic acid, uronic acid plus aldonic acid. Okay, uronic acid and aldonic acid gives us what? Lactones. Remember this? And N-acetyl tyl manosamine. Okay, N-acetyl manosamine. N-acetyl manosamine will give you what? It will give you the N-acetyl neuraminic acid, or it is called as a sialic acid. Okay, sialic acid, or it called as a N-acetyl neurominic acid. So N-acetyl neuraminic acid is used for it become the part of the glycolipid or the glycoprotein or the extracellular matrix binding interaction with the other component outside of the cells. So this is the role of that sialic acid, and it will increase your like skin life also, or because it is helping in the extracellular matrix, so skin will be always mature, like it will be more shiny, it will be more uh, matured, or it will be not going to be dyed without alkanes and all. So there are so many facts about the carbohydrate that we will read in the last video. So reducing sugars will be like Benedict test will used for the finding whether the glucose are there in our blood or not, or in urines also, or you can see urine, stool, or the blood. So what we are going to do in Benedict is the free aldehyde which are there in the sugar, as we know, that aldehyde at the terminal aldehyde which we are talking about. Okay, so that aldehyde is able to go for the redox reaction, that will go for the redox reaction, and which the cuprous ion will cupric ion will be converted reduced into the cuprous ion. It gives you the brick red color, and that is about the Benedict test. If the red color will come in the urine, then we'll find the person having the high glucose in their blood. So, how we can say if urine having a blood, sorry, more glucose? Can we say the blood also having a more glucose? Of course, because kidney will filter the blood only. Okay, I remember it. So all aldose monosaccharides are reducing sugar like a fructose and ribulose, and the polysaccharide which having an end without a glycosidic bond, and which don't have a glycosidic bond with the other carbohydrate, then it will called as a reducing end. Disaccharides we are going to see. So sucrose and the triholose are the non-reducing sugar. It means they are more stable in the nature. They don't used to be react with anything. Uh, they are not going to participate in the redox reactions and all. So they are more stable. That's why the sucrose is used for the that's why the sucrose for the storage and the transportation of the will be used for the storage and the transportation of energies and energy. So glucose and the fructose are the unit of the sucrose, which are bind by the alpha 1 alpha 1 to beta fructose. So why this is both arrows? Because they can change their places in both side. It can be possible to make this type of bond. Triholose, glucose, and glucose are the unit of triholose, and it is having a bond between the alpha 1 and alpha 1 carbon. Triholose are usually found in the hemolymph, as we already studied, and it serves as an energy or a storage compound, and as well as anti-freezing in some invertebrate. It will act as an anti-freezing in the some invertebrate. Anti-freeze in invertebrates. Okay, and serve as energy and storage. Serve as energy and part of and form hemolymph. Hemolymph. So maltose is the unit of maltose are the glucose and alpha 1 for glycosidic bond will be there, and lactose having lactose and glucose beta 1 and alpha 1 beta 1 and alpha 1 glycosidic bond you can see. Cellobios have the glucose and glucose beta 1 4 glycosidic bond you will see. Genetobios have the glucose and glucose beta 1 6 glycosidic bond you will find. So this is all about the uh, basics of the carbohydrate structure. In next video, we'll read the polysaccharides. So thanks for watching till now. We'll meet in the next video. Jai Hind. If you have any doubt, you can ask me. You can go for the links for the live classes, or you can find the related questions in the description. There will be link for the practicing questions in the description. You can go and find it down and practice these questions. Jai Hind, will meet in the next video.